All right. Listen, hey, right. Hey, we're done. All right. So we got. Where's the assignment today? Here we go. No. Don't look at that.
Oh, what?
I'll have to edit that out. Don't look at everybody's grades. Where are we at? So here's the assignment for today. Let me actually go and do the student thing. I've been liking doing that, where you get to see. Nope, that's not what I meant to do. Poor generic student. You wear your ID around your neck, and it has your ID number on it. I don't think that's like a secret thing, right?
I take it off.
I'm working mine out, like on the camera.
All right. So look, what we have, just so you know, the movements in space is still up from yesterday. I just left it up an extra day just in case anybody couldn't get it done. So if you still need to work on it, it is there. Today, we're doing measuring distances in space, and I have the reading assigned, which is distance within the solar system. So we're going to go ahead and open that up, and I will go ahead and open up the assignment also. So close your Chromebooks. And we're going to go through this. So basically, this is, again, just one page. I've been enjoying these. When we have like 3 or 4 pages, it seems like there's so much information. You can't really go through it. So these one-page ones aren't too bad. So how is distance measured in space? When we look out and we see the stars, we often talk about they're like, 50 million light years away. How do we know that? How do we actually get to that point where we can figure out how far away those stars are? Because it just looks like a point in the sky. And how do you do the math to get to the point where you can figure out how far away those are? So we're going to talk about that today.
Did you say 50 million?
50 million light years away? Yeah. Oh, there's stars that are a really long way away. Huh?
You know how fast light travels?
Yeah. Well, we're going to talk about that today. What gets weird is when you get to, we have found stars that are further away than in light years than like the universe is old, which doesn't make a lot of sense, but there's some complicated math to kind of explain that a little bit. But yes. So first they're going to start off with an astronomical unit, and they will ask you a question on the homework. What is an astronomical unit? An astronomical unit, or abbreviated AU, is the distance from the sun to the earth. That's what that distance is. And so when we talk about astronomical units, especially here in the solar system, it's a useful measurement, kind of like a mile. Depending on how you're moving around, a mile might be a really long way, or it might be a really short way that you don't have to go a full mile. Or to go to the next town over in Ennis, you might need what is Ennis? Like 10, 15 miles away?
It's like 6.
4,
6?
5.
4? That's not very far. All right, I thought it was further. But anyways, for astronomical units, the distance from the sun to the earth, if you're talking about Mercury or Venus, you're less than 1 AU. If you're talking about Mars, you're a little bit over 1, maybe close to 2. I don't know if it's written on here. It's not. But when you get out to the outer ones, you're talking about maybe 15, 20, 30 astronomical units because they're much further away. Now, how far is an astronomical unit? About 150 million kilometers. Remember, we're going to be talking about kilometers, not in miles. So 150 million kilometers is 1 astronomical unit. So they actually show you here the planets. Mercury and Venus are less than 1. Mars is about 1.5 astronomical units. Jupiter is about 5.2. Saturn's 9.5. Neptune out here is 30 astronomical units, and then Pluto would be even further than that.
Like 576.
Maybe not that far for Pluto, but it's going to be, probably maybe closer to 50. So distance within the galaxy, we're talking about light years now. Light years are 300,000 kilometers every second. And actually, that's a weird way to say it. Usually when we talk about light speed, it's actually this right here. 3.00 times 10 to the 8th meters per second. And so this is actually the normal way that we describe light speed. So it's 3.00 times 10 to the 8th, which is 3, 1, 2, 3, 4, 5, 6, 7, 8 meters per second. 300 million meters per second. Yeah, good job. So 300 million meters per second. They say 300,000 kilometers every second. But that is 1 Well, that's the speed of light. That's not a light year. That's the speed of light. Now, how far does that travel in 1 year? 9.5 trillion kilometers in 1 year. So for an astronomical unit, it was 150 million kilometers. For 1 light year, it's 9.5 trillion kilometers. So they even skip over a billion. They go straight to trillion for kilometers.
What's past trillion?
What?
What's past trillion?
Quadrillion and then quintillion. They go way up.
Like sextillion.
I think the biggest number is Googleplex, which sounds funny because it sounds like Google, and they might have taken their name from it. But
How many zeros is behind?
it's a lot. You can get into really big numbers, but we're not going to get into it now. Listen, we're not going to get into it now. So a light year is 9.5 trillion kilometers. It's about 63,000 AUs. Hey, don't be looking it up. Close your Chromebook. Well, it's not going to hurt you if it's close. So know that it only takes light from the sun 8 minutes to get to Earth. And so that's not very long. Light travels really, really fast. So let me go. The Milky Way is about 100,000 light years across. There's something specific I'm looking for.
So the
here.
heat that we feel when we step outside is 8 minutes old.
Not necessarily the heat, but kind of, yeah, because I guess you are getting heat from the sun. So yes, it is about 8.5 minutes old. Yeah, yeah. Yes, and anytime you look at a star, you're not seeing that light from right now. You're seeing it from however distance in light years it is away. And so you're looking at the stars in the past. You're looking at the sun in the past.
Looking at dead stars.
Pretty much everything you see is in the past, but for most part, the stuff that is so close to you, it's such a short time that it's not really going to matter. Hold on, we got to get through this. And then once you're doing the assignment, if you have questions, you can ask questions. But we got to get through this so you'll have enough time to look at the assignment. So the closest galaxy to us, the Andromeda Galaxy, which I believe I talked about, is going to hit our galaxy in the future. It's about 2.5 million light years away. So it is quite a bit, quite a good distance away. And when we see the light from that galaxy, it has been traveling about 2 million years, if that makes sense, because that's how fast the light travels or how far it travels. So we're seeing that galaxy 2.5 million years in the past. Probably not. I think we're talking about when the galaxy collides, maybe. Not in 2.5 million years, no. But when our galaxies hit each other,
like the sun of
possibly,
that galaxy
yes.
is moving towards us.
Yes, that galaxy and our galaxy have about a 50% chance that they will collide in the future.
What happens when stars hit each other?
That's a good question. I don't know that we've ever observed that before. It's probably not good for anybody who lives around there. So here's the main point. Hold on a second. Here's the main point that we're getting to. How do we see things that are so far out and actually know how far away they are from us? And if you've ever looked through binoculars or like a telescope or something, it's really hard to get a sense of how far away things are. Like when you go outside and look at the moon looks really close. You can see features on it. It's not that small in the sky. But when you actually see the distance that the moon is from the Earth, you would be surprised. It's a really long, far way away. It took the astronauts 4 days to get to the moon. And so it is a long travel, even if you're going really, really fast. So how we figure out that distance is called the parallax. And I tried to find a video, but parallax has now become a term for photography. And so all the videos now are about the photography. There used to be several good clips because the parallax comes into play on the football field and on the hockey rink. Every once in a while, you'll see a live play, and the running back or the receiver will stretch out, and it looks like they crossed the plane with the ball from the live play camera. And then they go back, and they get the camera right on the goal line, and you can see that they didn't. And the idea here is, depending on your angle, it's going to change how you actually see, the location that you actually see the thing in. So my example is, let's see, here's the line, here's your football. That's a terrible football.
Let me put some laces. So now you know.
And yeah, that's your goal line. That's your football. And if you're looking at a camera that's like down here at the 50-yard line, this is my camera. Boom. If you're looking at the camera down here from the 50-yard line, you're seeing, well, I didn't angle my camera right, but you're seeing it, and it definitely looks like the football across the line. Like, it's like, that's a touchdown. How could you argue any different? This is a dumb challenge. And then they come down here to your pylon camera.
They realize you have 3 centimeters.
Yeah, and they got the little camera in there, and they see down here, and you can clearly see green grass in between the goal line and the football, and you're like, that's not it. That's the parallax, and it's the idea that the position of the object you're looking at changes depending on your angle to it. And so this is actually a math concept. We use it to illustrate things in sports sometimes. The same thing happens with hockey, because in hockey, it doesn't have to break the plane. It's got to go all the way over the line. And sometimes it looks like it did, but then you get the goal camera and it didn't.
What does that have to do with depth perception?
Yes, and that's kind of what it is. It's depth perception. But how do you perceive things that are super, super far away from you when you can't really move that much? Especially if you think way back in the day, you couldn't just like hop on a flight and fly to the other side of the world. It would take you months and months and months to get there. And by the time you have, the Earth is kind of in a different position. So they're going to have a couple examples of this. Here's your thumb. Did you ever do the left eye, right eye thing? Mm-hmm. Like you put your thumb in front of somebody's face with your left eye closed. You move to your right eye and your thumb is completely the opposite way. That's the parallax. And so just that short distance between your eyes can change your viewpoint like that. And if we're really looking at something super far away, it might be a little bit harder, but we can get that done. So let's see if they have a better example down here. They talk about the parallax. Yes. So what we figured out here, if this is going to open. Oh, is this a video? I don't know that I want to watch a 5-minute video on it.
We should definitely.
Well, let's see.
How do you imagine astronomers calculate the space between celestial bodies?
Sorry.
Take a
We're not
look
gonna watch
at how
the whole
they
video.
rely on indirect measurement.
Oh, that's not what I meant to do.
That's
Hush,
exact.
hush, hush.
How do you imagine astronomers calculate the space between celestial bodies? Take a look at how they rely on indirect measurement.
So what we do is, we take a measurement from wherever we're at. We look at the star. We take precise measurements on the angle where we're at in the Earth, where it's at in the sky. We plot these points, and then we wait 6 months. Because 6 months from now, the Earth will literally be on the other side of the sun. So moving like from one eye to another, that's not enough. Moving like a couple miles down the street, you're not getting enough distance there to actually see things that are really, really far away. But if I move to the other side of the planet, so this is where I saw it the first time. I move all the way around to the other side of the sun 6 months later, and I look again, and I see it over here the second time. I do a little math, and I draw these rays back to my same position, and I know the star is right here. And so that is how the parallax works. It allows you to calculate the distance. So now we know the distance to that star because we can do our triangulation here. And we know how far away that star is from us and how old the light is because we know about light years. So I'm not going to let the whole video play. We're pretty much done with it now. Let me go back. So that is the parallax, and that's how we figure out how far away these stars are. And so it is just like a matter of geometry. It's a little bit of a math problem. It's not too bad. I don't know that we're really going to do it, but what they have here is the distance to an object is measured in parsecs, and the formula is 1/parsec. So they do have a problem in the assignment where they ask you what the distance is. They tell you the parsecs, and you just need to put it under 1. So you do 1 divided by that answer in parsecs, and that should tell you what the distance is. So that is going to be a question in the assignment. Now, what else do we have down here? So yeah, there's your sample problem. They have 0.076 arc seconds. And so your answer is 1.3 parsecs. That's how far away it is. Let's see. Peering into celestial sphere. To simplify this concept of where things are at, yeah, wake up back there. You slipped off your elbow, didn't you? To figure out where things are at, it makes it easier if we kind of put it in a reasonable kind of format. So imagine like a space globe. Instead of one big map that really shows everything all around the solar system, which would be immensely huge, you wouldn't be able to view it reasonably. Even putting it in a computer would take a supermassive computer. We put it on a projection around the Earth. So we have this projection, I forget the name so quickly, sorry. They call it celestial sphere. So you kind of put it on this globe out here, and you project the points out onto the globe. And so it doesn't really matter how far away they are. We can kind of see everything all together in a way. That's what the celestial sphere is about. So it says, to simplify that concept of observing objects in the sky, scientists devised the imaginary sphere that surrounds the Earth. It's called the celestial sphere. It's based on the false assumption that all objects in the sky are located in the same distance. And even though they're not the same distance, you can still use this to reasonably plot where things are. But this is kind of how we thought at the very beginning. Know that there's two different ways you kind of measure these in the sky. You have declination. Declination is analogous to latitude. So remember, latitude is like up and down from North Pole to South Pole. And then right ascension is like longitude. So that's like left and right to east and west. And they probably have a set point depending on how you go. So they break these up into hours, from 0 hours to 24 hours. Because how long does it take the Earth to spin around? 24 hours. And so even when you get into latitude and longitude, they use terms like hours and minutes and seconds because they break up the entire Earth into those 24-hour sections. Let's see. They talk about a couple constellations. I don't know that there's any questions about the constellations, but there are a lot of constellations. There's 88 of them. If you don't know what the Big Dipper is and the Little Dipper, I feel sorry for you because those are the easier ones, but you should be able to see the Big Dipper and the Little Dipper. I will say it's really hard to see both of them. You got to be like in a really clear spot because for a long time I wasn't able to see both of them, and then we went out to Washington and I saw both of them at the same time, and it like blew my mind. So if you ever get a chance to see both the Big Dipper and the Little Dipper, because all the time you go out and see, you'll see one of them. And you're like, I don't know, is that the big one or is that the small one? But when you see both of them together, you know. So go ahead and get started. I think I covered most of the stuff. If you have any questions, please let me know. I'm going to pause this video in case I need something else to add to it. If not, we will have a test Monday, and I'll actually send the email out soon to remind you all of that.